Hello everyone, this is Kayvon from MBT. In this session, we're going to have a simulation about battery cooling with two-phase nanofluid. As you may know, nanofluids could be used for enhancing the cooling process of electronics like batteries. So in this session, we have a battery cell that contains two inlet channels for the coolant. And in this channel, the coolant is contained with solid nanoparticles that make the nanofluid applicable for enhancing the cooling process. So we introduce a fluid type material as copper oxide, which is solid nanoparticles, and among the most important properties, we need to edit the material properties like thermal conductivity, viscosity of nanofluid, density, molecular weight, and we also take the effect of gravity into account, as in high values of volume fractions of solid nanoparticles, the gravity may affect the cooling performance. In the MSMD battery model and simulation setup, we're going to use a C rate of 10. The coolant inlet velocity would be 0.05 meter per second. The volume fractions of nanoparticles we use are 0.02 and 0.08. The total flow time would be 5 seconds, so we're not going to spend a lot of time on the simulation, and we just need to realize how to set up the simulation and have the result we want from nanofluid cooling. So, and the time step size would be 0.2 seconds. So in total we have 25 number of time steps for the flow time of 5 seconds. Now we go into the Ansys software and start the simulation. So now here we are in the Ansys software. We have generated the mesh before and just simply imported the mesh file. You can find the mesh file link in the description of this tutorial. So now we start the Fluent Solver. We use double precision and serial for processing. It's gonna take a while to load the mesh. It's a structured mesh with good orthogonal quality. As you can see, we have created some boundary layer near the walls to capture the heat transfer accurately. You can watch previous videos on how to create the cell geometry or generating the mesh. But now in the advanced playlist, we don't need to work on that section. So now in this simulation, we're gonna use the transient for the time. We're going to turn on the gravity as we said and have a value of minus 9.81. So the direction vector of the gravity would be minus y. Before going further, we check the mesh and check if the minimum volume is positive, so it's okay. Then we go to the tab physics and we turn on the energy equation. From the solution tab you can see that the flow equation and the energy equation are both turned on. Now we can import the MSMD battery model using define models add-on module, and we select number 8, the dual potential MSMD battery model, and press enter. So now the MSMD battery model is loaded, and we can go on to the models and turn on the MSMD battery model. From the eChemistry models we select the NTGK empirical model. The nominal cell capacity would be 14.6 amp hour, and the C rate we increase it to 10 in order to have the increase in temperature in a short time, and we need to simulate the cooling process and have the results in a shorter time. So from the model parameters, make sure that the initial depth of discharge is 0. For the conductive zones, we need to select the cell zone for the active components and the negative zone and positive zone for the tab components. We don't have any busbar components here. If you want to know how to create these zones, you need to watch previous videos on the elementary playlist or the intermediate playlist to see how to create these zones in Design Modeler. For the electric contacts, we need to select the N tab for the negative tab and the P tab for the positive tab. Those are the negative and positive tabs of the battery cell. And now we're ready to print the battery system connection info. Once we have done this, there will be a message of end of battery connection info, and we press OK. It says that available material properties or methods have changed, and we need to confirm these properties before continuing. It's actually for the material section. It says there's new material properties like UDS diffusivity is now available to select or edit. So we click OK and go on with the material section. In the materials for the fluid, we need to define water liquid as the coolant and also nanoparticles, which is also considered as a fluid type material in this simulation. So we open the material tab, and from the Fluent database we're going to import the water liquid. We simply copy it. So now we have the water liquid. Another material we're going to import is the aluminum solid. which is here. Okay. So now we have the aluminum solid, but the material we're going to use in this simulation is copper oxide. So we need to change the name and properties of aluminum solid. So we change the name to copper oxide. We give the formula as CuO. You need to search for the copper oxide properties. So we need to edit the properties of this material. The density would be 1020. The thermal conductivity of copper oxide is 33. The viscosity would be 0.01. And we don't need to change the UDS diffusivity or electrical conductivity. So we just simply save these changes and we can check it again. The name is correct, chemical formula is correct, density, thermal conductivity, and viscosity. So it's done with the fluid materials. Now we go to the solid materials to define the tab materials, positive and negative tab, and the middle section, which is the active component or the battery cell. So we need to edit the aluminum and consider it for the active component. So we name it as active material. We name it a formula as A_M. The density of the active material would be 2092. For the UDS diffusivity, we're going to use the option of defined per UDS. So for UDS 0, we select a value of 1.19 e to the power of 6. And for UDS 1, we select a value of 9.83 e to the power of 5. So now you can see that UDS 0 and UDS 1 are changed. So this is okay for the active material. Now we can select another material for the tab components. So from the solid type material, we select copper and copy the information, and we change the data as the name would be tab material with a formula as T_M. Density would be remained unchanged as the copper density. The UDS diffusivity for the tab material, we use the user defined function, which is the battery eConduct MSMD BAT. And for electrical conductivity, we give it a value of 1.1 e to the power of 7. So if we check again, the name is tab material, density same as density of copper. UDS diffusivity is the user-defined function, and electrical conductivity 1 e to the power of 7. So now everything is okay with the material section. Now we can go to define the multiphase model. For the model, we're going to use the Eulerian. The number of Eulerian phases would be 2, and we use the implicit formulation. Phase 1 would be the liquid water, and phase 2 would be the fluid type nano particles. So now we can have the phases here, the primary phase and the secondary phase. As I said, the primary phase would be water liquid. And the secondary phase would be copper oxide. We use the granular option for introducing this material as solid particle. We're going to use the partial differential equation for granular temperature model, and for the properties here we only change the value of diameter to 10 nanometers, or 1 e to the power of 8 meters. And that's okay with phase 2, or the secondary phase. So we check it again. The granular is on, the partial differential equation, and diameter is 10 nanometers. So now we're ready to go to the cell zone conditions to assign those materials to different zones. In the middle we have the cell zone, or the active component. You can watch previous videos on different sections of the battery, specifically videos on the elementary playlist would be fine. So the middle section is the cell zone. Fluid 1 and 2 would be 2 rectangular channels on the sides that the coolant comes in and cool the battery. The negative zone and positive zone would be the tabs, that one of them is negative and one of them is positive. So for the cell zone, we need to assign the active material, which is already chosen. For fluid 1, the phase is mixture, and that's okay. Fluid 2 is the same. For the negative zone, we need to select the tab material, which was the copper properties. For the positive zone, we also use the tab material again. So the material for the tabs are the same. Now we're done with the cell zone conditions, and we're ready to go to the boundary conditions. In the boundary condition, we need to define the velocity, the value of velocity of the coolant entering the inlets. So inlet 2 and inlet 1 are for the 2 channels on the sides. The flow direction would be along the positive x axis. So for inlet 1, we need to define the value of velocity for phase 1 and phase 2. For phase 1, we define the velocity only. But for phase 2, which is the secondary phase, besides of introducing the velocity value, we should define the volume fraction of the secondary phase, which are the nanoparticles. It defines how much of the volume is considered to be the nanoparticles. So now first for the phase 1 or the primary phase, we edit the values. So the velocity magnitude would be 0.05 meter per second. The temperature would be 300. And this is all. So now again for inlet 1, but phase 2, which is the nanoparticle, we select the same velocity of 0.05 as the velocity of primary phase. For the granular temperature, we give it as 0.01. The temperature would be the same, 300. And from the multiphase tab, we select a value of 0.02 for the volume fraction of nanoparticles. And that's all for the phase 2 properties in inlet 1. We define the same values for inlet 2. The velocity would be 0.05 for phase 1. Thermal is 300 for the temperature of the inlet. For phase 2, the velocity would be the same. The granular temperature is 0.01. Thermal is the same. And the multiphase would be 0.02. So this is all for phase 2 of inlet 2. You can also change the outlet pressure, for example. But in this simulation, we don't need to work on that. But if you have any experimental data or any boundary conditions based on your simulation, you can check those out. So now we can define a report plot for reporting the cell temperature and see how the coolant is going to help us to cool the cell of the battery. So we define a new report. We use a surface report as the facet maximum. We name it as cell max temp. We use the temperature for the field variable and wall temperature, and for the surfaces we use the wall cell zone. We report the file, report the plot, and print the console. And that's okay for the reports. So we can see that we have a CellMax report file. Now we can go to initialization to initialize the solution. We use hybrid initialization. And we initialize the solution. It's going to be a two-step initialization. First is for the flow, and second would be for the MSMD battery model. So the battery model is also initialized. Now we can go to run the calculation. Before that, you can check the case to see if the Fluent solver is going to recommend you for some additions. It says that consider using higher order discretization for improved accuracy. You can use it for your own simulation. This is not the case here. So we go with the setup. For the number of time steps, we use 25 time steps. The time step size would be 0.2 second. So the total flow time would be 5 seconds. The maximum iterations per time step we selected as 10, which is enough, and we'll get a converged solution. And now we're ready to start the calculation. This is gonna take a while, so just relax, and we'll come back when the calculation is finished. So as you can see, the calculation is complete, and the last iterations are fully converged. Now we can see how the temperature variation and the velocity inside the cooling channels all look like. So we go to graphics and contours. We select the temperature of phase 1, the static temperature. Phase 1, which is the water liquid. We define a new surface in the middle of the battery cell, so we give it a value of minus 0.015 for the Y values. We copy the same value for all Y values. We give 1 to X0 and 1 to Z2 and create. So this will be a plane in a constant value of Y. And now we can select this plane and display the temperature. So as you can see, the temperature will go up to 337, and the flow direction is positive direction of x-axis. So as you can see here, by passing the water liquid or the two-phased nanofluid through the channel, the boundary layer will show us a thermal boundary layer grows in the channel on both sides. You can also check the vectors of velocity. So we select the velocity and velocity magnitude of phase 1. We select the same plane we've just created. So you can see that the inlet velocity, which was 0.05 meter per second, will go up to 0.08 because of the heat transfer and because of the growth of the thermal boundary layer. And as you can see, by passing through the channel, the velocity will increase. So this was the simulation with a volume fraction of nanoparticles of 0.02. If you repeat this simulation with a higher value of volume fraction of nanoparticles, you can see that by increasing the volume fraction, the heat transfer will increase and the cooling process is much better. So please repeat the simulation with a value of 0.08 for the volume fraction of nanoparticles or the secondary phase, and then we compare the results and see what happens. So now here we are with the results of the temperature variation with time for two volume fraction values of 0.2 and 0.08. So as you can see, by increasing the volume fraction of nanoparticles, the maximum cell temperature will decrease. And after 5 seconds, you can see that there would be a 5 degrees difference between the two simulations. Actually, the maximum cell temperature will decrease by 5 degrees after 5 seconds of simulation with a C rate of 10. If you want to increase the value of volume fraction, you can increase it up to 0.15. That it's normal in nanofluid cooling applications, but the normal value is something between 0.05 up to 0.1. I hope you enjoyed this video. If you have any questions, please leave it in the comments and share this tutorial with your friends and give it a thumb up if you liked it. Have a good time.